Okay. Okay, got it. Okay. So, hello everyone. So today I will be talking about the ReactFF. ReactFF, which is one of a kind of a reactive force field. So before going into the details about this reactive force field, I just want to give a quick review about what is a force field. So the force field is used to estimate the forces between the atoms or the between the molecules. It has some kind of a functional form which have a set of parameters and which is used to calculate the potential energy. Now this force field that we are talking about, we can calculate. Now you already know that the forces are the negative gradient of the potential energy, and this potential energy is a very difficult quantity to calculate. So in classical molecular dynamic simulations, we use the empirical force field, and in the quantum mechanics we solve the Schrodinger equation. Like in classical MD, we use the empirical force field. Yeah, here FF is refers to your force field, and then in quantum mechanics we solve Schrodinger equation to get this potential energy. Now we need some link between uh, these two systems to represent some of the quantities which were absent in both of these. I will tell you about this. Like first we will quickly discuss about this empirical force field, like what happens in this empirical force field. So the potential energy is related to the internal coordinate of the system in this empirical force field. Therefore we can write down the total potential energy of the system is the summation over I from 1 to your bonding parameters plus I1 from your angle plus, okay, I should write it down here only, summation I from 1 to and your dihedral angles plus your non-bonding parameters. Here your NB refers to non-bonding parameters. So this comes under the category of your bonding parameters. And there are your non-bonding parameters, which are your Coulomb potential and van der Waals forces. So this is the journal form. Now, in the classical force field, I should write it down with some black one. Now in classical force field, all these bonding parameters are treated as your harmonic potential. Where your Kb and Ka refers to your force constant with respect to your the contribution from the bonding and the angle parameters. So now because in classical force field the all of these parameters are considered to be as a harmonic potential, therefore this classical force field has a disadvantage that it cannot include the parameters, or it cannot include the bond breaking and the bond formation of the molecule. Bond breaking and bond formation is not included, which is a disadvantage of this classical empirical force field. And all these empirical force field have some set of parameters that are to be calculated from the either from the experimental data or from the ab initio calculations. Now, all these non-bonding parameters, the van der Waal and the Coulomb potentials, have the general form as it is, as we know that. Now I'm going to quickly talk about this quantum mechanical from the quantum mechanical perspective. Like first I've talked about this classical molecular dynamic simulation. Now I'm going to talk about this quantum mechanical, yeah, or quantum molecular dynamic simulation, that in which we solve the Schrodinger equation. So from a quantum mechanical perspective, the system at a fixed time can be parameterized in terms of your coordinates, and the coordinates of the nuclei and their relevant electron. Now, by applying your Born-Oppenheimer equation, Born-Oppenheimer approximation, Oppenheimer. I've written down the spelling wrong. Now, when we apply the Born-Oppenheimer approximation, so one can think that the nuclei are fixed at some instantaneous position. So this way we can convert that, or this way we can write a time-independent Schrodinger equation for many body wave function, of the electrons, and then the time-independent Schrodinger equation is solved using the DFT to obtain the energies. The time independent, your time independent. I'm not going into the details. I'm just telling you like what happens in all this ab initio molecular dynamic simulation. So we solve this time independent Schrodinger equation with the help of DFT to get the energies, and then these energies these energies are considered to be a function of the nuclear coordinate that we have fixed earlier, and thus it can act as an interatomic potential that is needed to compute the forces. So by computing the gradient of these DFT energies at a fixed point with respect to some nuclear coordinate, the forces are obtained, and the nuclei are moved accordingly to get to the next step. And this DFT processes keep on repeating until we get the potential. So we have another method, which is your QMMM method, which is your quantum mechanical molecular mechanics method, in which what you do, if you have a very large system, and you can choose the choice of your system, and you treat that system quantum mechanically, and the rest of the system is treated as classically. Now, there are some disadvantages associated with this quantum mechanical method or the ab initio molecular dynamic simulation. This is the most fundamental method, but it is quite expensive and it can work only for small system. So the disadvantage is it is quite expensive and it works only for small systems. Like I can show you one. Where it is? Okay. Is it visible?
Yes,
Yes.
yes.
Okay. So as you can see, like we have the quantum mechanical method in which we have the ab initio dft or Hartree-Fock method. We can solve it by the like it includes all the electrons and bond formation. It does include the bond formation, but it can be applied only for the for the small system. It is quite expensive also. Then we have the another method which was I've described earlier, the force field method, the empirical force field method. It needs to be trained, and it is much cheaper than the quantum mechanical method. It can be applied to a large system, but it does not include the bond formation. But it does not. Where is the pen? But it does not. Oh, but it again, I'm emphasizing that it does not include your bond formation, and it does not include bond formation and bond breaking. So we need some method that can include some bond formation and the bond breaking, and it does not take too much. Like this quantum mechanical method takes too much time to complete even a picosecond of reaction. So we need some alternative method. So in that regard, some in 1988, around in 1988. Oh my god, what happened? Sorry. So in 1988, J. Tursoff gives a new empirical approach for the structure and energy of covalent system. So this was, as far as I know, this was the first paper I've encountered in which they have include the bond formation term into the potential term or parameter. And after this around 1989, Burner Burner and what was I forgot the scientist name, but they gave one potential called Erebo potential, and these uh, Tursoff, Burner, Erebo are called the first generation reactive force field, because they included the bond formation parameter into the total potential energy. Then we have some other uh, COM and MEAM potential. These are called the second generation reactive force field. So in the COM, the this is the charge optimized many body potential, and this is modified embedded atom method. I will not go into the details of this because this will require 2 more hours to cover all these potentials. But I will just give you the form of this potential. The COM has a form of this. So the total energy is the summation of self EI self QI, which is the self energy of the atom, plus summation over this is the bond order potential between atom I and J. If you have some other atoms I, J, so this is the E short refers to your the bond order potential between your atom I and J. Then we have the Coulomb potential. The polarization. Then we have the van der Waals contribution. Here the E barrier. This E barrier is your charge barrier function. And this E corrected is your angular correction term. So now after this, these two are called as a second generation reactive force field because it includes the charge optimization, unlike this first generation reactive force field, which only included the bond order term. In the first generation reactive force field, they have included the covalent terms, and they did not focus on the charge optimization or the polarization of the system. So in the second generation reactive force field, they focused on the this charge optimization of the many body potential. They have equilibrated the charge using the electronegativity equalization, which is termed as QEQ also. This is the QEQ method. Or there is another method to equilibrate the charge in the system, which is EEM method. Electronegativity equalization method. They both depend upon the hardness, electronegativity of the atom. Now, after all these, we then in 2000,
Deepika,
yeah,
I
Vanshika.
want to interrupt small.
Yeah,
There, go to the above equation that it is
yeah, yeah.
there. I want to understand means
Mm-hmm.
uh, how it takes into account the bond breaking and bond formation event. That EIJ short.
Mm-hmm.
This is the term where it's
Mm-hmm.
basically determines the bond breaking and bond making.
Okay. So Banshida, here the
Mhm.
EIJ short, RIJ, QI, QJ. Here, we have this is called as a bond order potential. So when the bond is broken, so this energy contribution. this will have some energy contribution in it. Like it has some explicit form of like bij and some eta n to the power n minus 1 function kind of thing. So this bij, this will take into account that bond breaking and the bond formation of the molecule.
It is a step function like thing, or it is a some
Hmm.
continuous transition? Means I want to, means there is a, means
Hmm.
depends on, suppose let's say qi and qj. Q are the charges, na?
Hmm.
Qi qj, it also depend on charge, but for
Hmm.
simplicity let's consider it is rij, the function
Hmm.
of rij.
Hmm.
For some rij value it is one bond, and some other rij value it is other bond.
Hmm.
Okay, so it is a, means dis, means discrete jump, or there is continuous from one bond to another bond. Means how it, how this function looks like, means.
Actually, there is some like, because it is derived from the first generation reactive force field, so there is some cutoff function also, so that the potential ranges between the 0 and 1.
Mhm.
And this bij has a very like how can I explain, uh, it's not a discrete kind of thing, but it is a continuous thing, but it is for very a short range of period. Like uh like if I give you some example, like in the carbon up to 2 angstrom we can observe the transition state. Up to 2 angstrom of distance if we'll calculate, so we can observe some transition state. But in this, because it only focuses only the short range distances, it cannot capture those transition states.
Okay.
Yeah, so that was one limitation of this kind of force field.
Okay, means in, means it is
Mhm.
some kind of, it is analytically, for analytical
Mhm.
treatment it makes, means some continuous, but practically
Mhm.
it's discontinuous like a behavior. Means either.
Yeah. Mhm.
And one more thing, this barrier,
Mhm.
means could,
Mhm.
barrier depends on this charge. So there is
Mhm.
some restriction on this charge. That's could you physically, this E
There is
barrier QI,
mm, whether there is some restriction
means
on the.
barrier means,
Mhm.
means those zone is forbidden, means
Hmm.
that's we call barrier generally. So it you written that it is function of charge.
Mhm.
So there is, unlike means means some polarizable cases also. Uh,
Mhm.
there are, if we do not consider this charge density, if we consider, means if we
Mhm.
does not consider any screening, like Thole screening, there are many screen.
Mhm. Mhm.
So
Yeah.
there are
Yeah.
spurious, like charge, means two charge, means
Mhm.
comes together very close to point charges, then there will be artifact.
Mhm. Mhm.
So something
Oh,
like that, this kind of
oh,
thing
yeah.
is.
Yeah. There was some correctional term also present in this. I can't recall its name, but there was some correctional term. What was its name? Mm,
Means my question is that barrier is connected to those kind of thing. Means I want to, I was just imagining
mm,
barrier on charge, means there, if we consider the point charge,
mhm.
2 point charge, if it comes very close, and if we calculate the
Mhm.
repulsion and all those polarization thing,
Mhm.
those result, means those are not
Mhm.
classical charge. But if we
Yeah, those are not
consider it
classical.
classically at this close distance,
Mhm.
so the result might be very very erroneous.
Yeah.
So that's why this screening actually Thole came up with the, with this screening scheme. So
Mhm.
there, uh, uh, I was
Mhm.
thinking the barrier might be related to something like that. Means if charge,
Mhm.
then also, okay, in the Thole screening there is also Rij dependent. Means this charge actually, the
Mhm.
screening depends on this after a particular distance. But
Mhm.
here you have written that it depends only on one charge. So
Okay. Mm.
Okay, so
Yeah.
For
Actually,
Deepika.
mhm.
So here, what does barrier what represents?
Oh, this is the charge barrier function.
I mean, physically, this
Charge.
is my same question. Physically, how?
Actually, yeah, actually, I have to like I have to look into it because uh,
Yeah, yeah, no problem. But
I cannot imagine like what's happening. Like what was this quantity? The charge barrier quantity. There was one function of this form, the charge barrier function. What was it?
Well, I have one more question. Is my maybe
Yeah.
related to that or not related
Mm-hmm.
to that? Means this E is total potential.
Mm-hmm.
Okay. So
Yeah.
this means when a bond is formed, then
Mm-hmm.
it will be harmonic, close to harmonic. When a bond,
Yeah, close to
where
harmonic.
it
Yeah.
is, in which term it is considered, in which term it is included, that behavior means is self is only one. It depends on only one atom, no?
Yeah, it depends only one atom.
So where it is
Mm.
polar, if van der Waals is okay, van der Waals interaction, Coulomb interaction. So this kind of harmonic thing means angle in an angle variable and bond distance variable. E is the total potential, na? ET means
Yeah,
everything.
yeah. ET is a total potential. Yeah. I guess that was included in this short like
Okay, okay.
the bond order potential, because the bond order, because when we talk about this reactive force field, these bond or like when we calculate the bonding parameters, they are also correlated with the angle and the dihedral angles also, depending upon that bonding parameter.
Mm-hmm.
So they are correlated with each other.
Okay, those are included in sort.
Yeah. So because
Vanshida,
Mm-hmm.
actually, I think the harmonic bond potential, the dependency on Rij, I think that is breakdown into different terms like short range plus Coulombic term plus van der Waals, like this term. So all these terms combined will give the bond potential, I think.
Oh no, but it is
hmm.
that we could not
Hmm.
think. Means this means previous this force field potential.
Hmm.
There is bonded interaction and non-bonded interaction. Means
Yeah, yeah.
empirically, if we want to treat the system, means the bond harmonic vibration we have to explicitly mention somewhere. Means in some uh, uh,
Hmm.
means I think it is short. Means Coulomb does not give, could not give this,
Yes, yes, cool. Hmm.
not give this thing. Mhm. And in ab initio, it is the interaction. Means it is due to this Coulomb operator that gives the vibration, but not.
Actually, this calm potential is derived from this tors of potential. So this tors of potential has this explicit form like E is equals to summation over I EI, which is equals to half of I where I is not equal to J VIJ. This VIJ is the bond energy.
Mhm.
I'm just telling you like so I should use. So this Vij is equals to, this is some cutoff function, and this is to control some how can I call, wait a minute, Fr Rij plus Vij f of a, okay, this a was capital Rij. So here this is the repulsive pair potential. This has the explicit form of the repulsive pair potential. This was the attractive pair potential, and they have the form of Mm. And the most important quantity in this was this Bij, which will measure the bond order. But again, this Tursov potential was only like it has a limitation that it only valid for the, like it only included the covalent part. It does not did for the, like for the charges and all. So, and this comp potential, it is
Deepika,
derived from, yeah.
just scroll up. Yes. So here,
Mhm.
for this, your EI is looks summation over single particle.
This is the component wise contribution.
Then how? I mean, how can it be? You know, here in the second is equal to Vij.
Mhm.
So summation is over I only, na?
No,
Okay.
no, it is a half is
Yeah.
considered
Half.
not so to exclude the double counting. So you are taking into account the interaction between all all atoms between like all atom number 1 and atom number 2, let's say. So you are dividing by 2 to exclude the over counting.
So it gives this bond order, right? Vij.
Which, this Bij, yeah, this will give you the bond order. But again, it has a very complicated form, so I didn't include it.
Ah, that's fine. Okay, you continue.
What is FC, Raj?
Banchita, it is a cutoff function to limit the range of the potential between 0 and 1.
Okay.
Yeah.
And AIJ has any role in bond order? Yeah.
It was just to control the, like if it overshoot, so it will control the value of that overshooting.
Okay. Means whether there is any bond, it depends on this function, FR and FA. Okay. Means FA, if FA is, if Bij is very large, then it will create a, means FA will, means FA contributes more largely. So then,
Yeah.
then it will form a bond. Means I'm physically just understanding this equation. So, okay, means it takes into account is if this is bond is formed or not, but other these harmonic vibration and all those things, those are not included here.
Yeah, all those things were not included.
And this part actually means this Bij, the same thing means is included in your self part. Go to the com potential Bij. It's some sort of this thing included in the short part here. Means some, of course, some with some modification, but the functional from.
Yeah, it should be there, because if this Bij will not be here, then there will be no benefit, like there will be no use of this equation. Then this will be not called as a reactive fulfill. So there should be, I guess, this kind of Bij function in this.
Okay,
No, Deepika, she is asking whether it is included in self or short term.
Okay. No. This will be included in the short term. This will be not included in the self term, because the self term is for per atom. This will be defined as a self energy of an atom.
Sorry, one more question. What is the self term? I initially.
This was the self energy of an atom.
Self energy, I know for Coulomb case, then we have the self energy, but you written in another term. So self energy means I could not.
I think once it's
Okay.
included in self only.
Okay.
Mhm.
Okay. Okay. No, no. I guess
Included in self one only.
Now, self means the energy coming from where? Means in force field, normal force field, we
Mhm,
just write in, it depends on ij, but here
mhm.
he considered all those other terms separately. Self energy,
Actually, I don't think so. It was included in the self energy because um, it was some ionization energy and some yeah, some ionization energy. I guess it was. So I don't think so that this Bij term was included here.
okay. But normal force field also there is no self term. Means
Mhm.
if we write Coulomb term separately, Coulomb self is
Mhm. Yeah.
different, but normal force field there was no self term. But here in the reactive force field, we need a self term. We have written.
Mhm. So
So,
also I will check Vanchika this.
okay. Means
Yeah, I will check and then I will get back to you.
okay.
Okay. So so then coming to the okay. So one thing more. So the next time when I will give again then again when my term will come, so I will explain this calm potential in detail. Okay, then it might will be clear to you. So now coming to the ReactFF. So ReactFF is your reactive force field. This is the third generation reactive force field. It was like it came into existence like not the existent is not the correct one, but the first paper was published by Van Duyn in 2000, and it was first introduced for the hydrocarbon atom for the hydrocarbons. Now, because this reactive force field is totally dependent, it is totally dependent upon the bond order. Okay, this is totally dependent upon the bond order, and it has an explicit form. Like if I can show you right now, here it was where it was. Okay, so this was the for bond order. Okay, so I'm sorry I couldn't write down it because it was okay. So as is it visible?
yes, it is visible.
Okay, so this reactive force will totally dependent upon your bond order, and the total energy of the system is a contribution from your bonding, like from the bonding energy. This OVER is your over coordination parameter. This is your under coordination parameter. This is your contribution to the energy from the valence atoms. This is the penalty term. E pen is the penalty term. E torse is your torsional terms. This is E CONG is your for conjugated atoms. This is your non-bonding terms, the E van der Waals and the E Coulomb. So this total energy of the system is a contribution of many small parts of this energies. So now every contribution like the bonding over coordination, under coordination, valence angle, or this penalty, torsional, and everything, it has its own functional form. So before explaining this functional form, I will quickly give you like how it works. So in the reactive force field, we have some atomic positions. From this atomic position, we determine the charges, and this by determining the charges, we use the QEQ method, which is your electronegativity equalization method. Then from there, we get this Coulomb contribution to your energy, and from the atom position we can get the van der Waals contribution. And also for the bonding parameters, we first determine the bond order. This bond first we determine the bond order, and according to that and according to this bond order, we correct this bond order for the local over coordination. Like it can happen that it can overcount some of the bond it can overcount some of the bonding parameter if the atoms are too close to each other. So we need some correction for it. So for that we need one correction term, which is your over coordination parameter. Then these angles and the torsional parameters are related to the bond orders. So from there we get the we determine these angles and torsional parameters. And there are some system specific terms. What is the meaning of this system specific terms? Like if you want to calculate the heat of enthalpy, entropy and everything, so you need some other parameters, so you can include those parameters also, and from there we get the total energy of the system. Now here you can see all the green colored elements have or for the all green color elements we have the reactive force field parameters, but for the violet colored elements, we still we didn't have any reactive force field parameters. Now I'm going to talk about like what are these bonding parameters and how it is dependent. So this is the first part. So the first part on which the system on which your system's energy was dependent upon your bonding parameters. So here we can calculate it like the your BOIJ prime is equals to exponential PBO1 RIJ. Okay, these are there are three exponential terms. Each of the exponential term is dependent upon your bond order, and the first term is for your sigma bond, the second term is for your pi bond, and the third term is for your pi bond, your second pi bond term. So and this full equation is for your is derived, like this can be a general equation, but it is here the specifically mentioned for your carbon bond. So one advantage of using this what it called this reactive force field, which is your bond order dependent, which is a bond order dependent, and this is a third generation force field. So it is different from your first generation force field, as that if you have the 2 angstrom of distance, as you can see, up to the 2 angstrom of distance you can still have a bond order. So it can calculate your long range bond order corrections, like up to long range bond order it can calculate, and in which you have the in which you can like significantly see the transition states also. But earlier for the first generation your first and second generation reactive force field, that was your short range what it called short range bond order potentials, where you cannot observe for a very long distance. So this was one advantage of using this reactive force field. Now it have several parameters, like this was the first parameter for your bonding for your what it called your bonding parameter. Then it can also overcount also. How it can overcount? Like if you see here, so this is the my cursor is not visible now.
No, no, no. Your cursor is.
Okay. Is it visible? No, 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 no. From near here, it cannot be seen. Okay. Then, do we like anybody know? Do we have a pointer in Zoom or something like that? No. Okay. Fine. Let me do one thing. Okay. Okay. So this is just for an example purpose. Okay. So I'm talking about this over coordination parameter. So what happens when it will calculate your bond order? It if this hydrogen atom is very close to this carbon atom, it will calculate some bond length. So this bond length, because it is very near to it, so but they are not in a so it will calculate some random bond length, and it will show just like, because it is dependent upon the bond order only, and the bond length is your is related to your bond, and bond order is related to your bond strength and the bond strength and the bond length. So it will just give it just a random bond length to you, and it will just show that these two bonds are also that like these two bonds are like these two atoms are making some bond. So it will just give some random bond length to this parameter, but in actual they are not making any bond length. So what happens, so what happens in it, so like here, as you can see, the first and this hydrogen have a bond length of 0.40 0.40. So it just overcounts this bond length, but anyhow this doesn't have any, like they are not related, so they should not be in the bonding parameters. So to correct these factors, they have these equations, which I'm not going to explain because these are very because these are very large equations. So they reduce the overcounting of this bond parameters using these equations. And also for the same case, it can still do like it can still do something like that. It can calculate the bond length very short. So in that case, we calculate the under coordination parameter, which can given by this equation, like the, if you can see the 7a and 7b. And then we have some valence angle terms also, and we have several equation for these valence angle. You can, and these all are dependent upon your bond order. First you have to correctly calculate the bond order, then all other parameters will calculated eventually.
Hello.
Yeah, hello.
One doubt I have. Can you go to the a little up, page up?
Mm-hmm.
Yeah, that's it. So that E under that we have the parameter term for E under equation on your right.
Okay.
That
The
in this
equation, yeah.
expression there is P another P under parameter term. So this is a constant value. This P under.
Where, wait a minute, this P under. Okay.
Yes. Similarly, you have P over and P under. So
Yeah. These will also be a constant terms.
okay. So these are will be
These
different for different system or will be same?
no. This will be all for the same system, and they will all like, and because this reactive force field have a different parameters for each element. For
Hmm.
each element we have a different parameters. So it will depend upon your element.
Okay.
Yeah.
And this gamma term is in the exponential. expression.
Okay. This gamma term. Okay. Then I have to explain you this over coordination term. This gamma terms come from here. This like if you can see here the valence I plus F2, the 3D equation. You can see this is also a parameter, like some variable, I guess. No, not the parameter, but some variable. This valence I plus F2 del I prime, then del J prime. These are all.
Okay.
Yeah.
So you have BOIJ, the 3A equation that I'm looking at. So this BOIJ 3A
Mhm.
equation, you have
Mhm.
another BO prime.
Mhm.
So the first bond order equation that you showed, that initially you have to calculate the bond order. That was
Yeah.
BO prime or BOIJ?
Actually, it was BO prime, I guess. Yeah. BOIJ prime.
Okay, yes.
Yeah.
Okay, so
Your
this is
total bond order, yeah, your total bond order will be your bond order contribution from your sigma pi or the double pi bond plus the
mm,
over coordination term, the energy contribution from the over coordination term.
and after this BO prime, once calculated, you look into the under
We
and
are
over coordination. And
we are
then correct it.
calculating. Yeah, you are calculating the over and the under coordination parameter. Then that will all add up and will give you the corrected bond order.
And that is why you are multiplying some function with BO prime
Yeah,
in your
yeah,
BOIJ and correcting the bond order equation. Okay.
yeah.
Okay, fine.
And what is delta? Means I am
Mhm.
still looking those
Mm.
things. What is
Okay, okay,
delta I? Delta
okay.
is
Yeah,
capital delta inside.
yeah. I'm telling you. So this delta i's are the degree of deviation from the from the uncorrected bond orders. Like you can get this like this here. This delta I prime term here.
Okay.
Yeah. This will be from your uncorrected bond order terms.
Okay. Valence I, VLI is
Yeah.
different means we have some reference. So
Sorry. Yeah. We have some reference. Like this reactive force field is a combination of all the first generation and the second generation force field. So
okay.
they have like the so many equation and the so many parameters in it to
Yes.
define each and every each and every term.
Okay. Means if it is written that it's valency means we
Mm-hmm.
have some predefined valency.
Yeah, predefined valency. Yeah, like the for carbon atom it is 4.
Okay, there they count means
Mm-hmm.
how it deviates from its predefined
Yeah.
valency.
Yeah, Manchita,
So,
you're
delta
correct.
phi.
Mm-hmm.
Okay, it is over coordinated, then it is some sort of a smoothen function corrected by means
Yeah.
in the three equation 3 means there are
Equation 3. 3. Okay.
equation 3. How it
Yeah.
is corrected means the deviation.
Yeah, the deviation.
Okay.
And in the same way, we have some in the same way we have so many parameters for this for every term for the angle parameters, and then we have the torsional angles. If you have a conjugated system, then for that conjugated system you have some parameters, and to include the non bonded your van der Waals interactions and the Coulomb interactions, you have this form uh, which is just a distance corrected Morse potential, and then the force field is optimized uh, just using the one parameter search technique, and you'll get this force field. But this force field has where it gone. I want to show you something like the functional form of this. Okay, so the right now I'm going to show you a typical reactive force field parameter file, like how it looks. And this is a typical This is a second generation water force field file. So first of all, it has some journal parameters around how many that was 39 or I guess 40, some 40 journal parameters. It has some, like you can see the over coordination parameters that was already predefined for a system, like because this is a water, so there will be some over coordination parameter. Then we have valence angle conjugation parameter. Again, there are some taper corrections also. And if you have a double bond, then the double bond angle parameters for that double bond, for every bond you have one over coordination and one under coordination parameter. And for every torsional or your angle parameter, you'll again have some over coordination and under coordination parameter. You have the cutoff for your bond order. Then we have the van der Waals shielding and all. And then the main part comes here. So this is reactive force defined parameters element wise. So like for hydrogen atom, this is for the bonding the first part, the first part of the system. Okay, where is a, okay, I cannot use the cursor. So the first part 3, the number of atoms, you have some how many it was, 2 3 4 5 6 7 8, okay 8 okay 32, okay, so 32 parameters per element. So this is the typical your force field parameter, reactive force field parameter file for your water 2018, for water 2018. And the upper OHX, these are the bonding parameters. And then these are the bond lengths for the corrections. And then we have the off diagonal terms, there may be some off diagonal terms for it. Then the angle parameters, 6 angle parameters. Then we have the torsional parameters and for the number of hydrogen bonds. So this was your typical reactive force field file. And now this reactive force field have like this reactive force field was started from what started developing from the hydrocarbons. Then it developed for your silicon, oxygen and hydrogen. And after that it was developed for the nitramines. And now it can be applied to any part of your like most of the part of your system, like for the aqua system. And specifically it is used for your metallic systems and all. So for aqua system, it's still in a progress, because for water it was easy to define all the parameters, but for other system it required more parameters. So it's still in progress. And that's it. And I've taken all these images from this reference. So if someone wants to read about the reactive force field, and so this is a very good review paper, you can go through it. Yeah, Banshida, I'm done. If you have any question, you can ask me.
Okay, Deepika,
Yeah.
one small question. While you were telling about this ab initio simulations, you mentioned that these energies are calculated on the fly, like for a particular configuration, you solve this linear equation while nuclear positions are fixed. So my question is then how your nuclei are moving, and means when they are moving, nuclei are also moving along this simulation trajectory. Then for that moment, this translational moment, how do you solve it? Classically or quantum mechanically, or how do you do that?
We use the classical Newtonian equation of motion, but we like calculate the gradient of energy. No, not gradient of energy. We calculate the gradient using we calculate the gradient, and like then we get calculate the gradient with respect to your what it called, the nuclear coordinates that you were fixed earlier, and then you just keep on repeating that. You'll get a new coordinate, you'll get a new energy, and then you'll calculate again. I guess I didn't answer your question correctly, or but the
Okay, is it your question that how nuclei moves, or means Ravi?
Yes, Mansi.
Yes, means yes, she told it correctly that at particular position at any instant of time, we get a particular form of potential. If I get the potential, then I can calculate the potential gradient at that point.
No, I'm actually just asking that these kinetic energies are calculated classically, no?
No, kinetic energy. No,
No kinetic.
Kinetic energy is kinetic energy, because electrons are solved using the potential is solved by this time independent Schrodinger equation for electron.
Right.
Nucleus are moved using this Newtonian classical.
Classically, no? Yes.
So
That's what I was.
okay. And here actually you should not call it classical molecular dynamics versus quantum molecular dynamics. This is not correct phrasing. This molecular dynamics versus DFT based or ab initio based molecular dynamics. Because in both cases nucleus are moving classically.
So I just give you an overview about the reactive force field, like how it works. But I guess next time I will explain you in detail that how the charges are equilibrated on in this reactive force field, because that is a very important part of this reactive force field.
Yes, it is definitely not a one day discussion or today. Means the involved things are there. You just saw today the overview of this force field.
Yeah.
This is a good starting point, means for others, for us. Okay.
Okay. So, like, if you have any question, you can ask me, or I will share one review paper and one very basic paper of J. Torsoff which was published in 1988, which is a very good paper to start with. So you'll get like how they have included the covalent, how they have included this bond order part in the reactive force field. So that's a very good thing. And one thing I forgot to tell you, like this the quantum mechanics, like if you use the ab initio simulation, it will take forever for you to generate even a 1 nanosecond of trajectory. But if you will use this reactive force field, it is 50 times slow. It is still 50 times slower than your your empirical force field, but it is very faster as compared to your ab initio molecular dynamic simulation, and it will give you results which is comparable to your experimental results, or because the data because the parameters you are because you get the parameters, they were trained on these DFT based like the trajectories you get from, or the parameters you get from this DFT calculation, they were trained over those parameters. So still it is faster than ab initio molecular dynamic simulation.
And Deepika, are there any comparison with the machine learning based potential on this reactive?
Okay. Yeah. So that's a new domain. Like I'm seeing there are paper from Beller, I guess from Beller. He compared this reactive force field with this machine learning potentials, and that was very interesting.
Means I want to just
Mhm.
want to their conclusion. I want to.
Mhm.
Is
Yeah,
it
yeah, that,
till
yeah,
now, is it
and
faster
mhm.
or slower? This reactive force field for a
Yeah, yeah,
particular system. Okay.
yeah. But still, still in if you'll use a machine learning based potential, you still have to again do all the things. You have to train the system and all. Like this reactive force field is okay if you know, if you have the parameters for an element. But if you don't, like, and it also these reactive force field parameters are different for your combustion. For your combustion reaction, the reactive force field parameters are different than your condensed phase system. So you have to choose wisely which force field parameters you will be using. If it is available, if reactive force field parameters are already available, then it is easy. But if they are not, then you have to train the system, you have to generate all those reactive force field parameters, then it will become very difficult.
Deepika,
Mhm.
so what was their conclusion in terms of accuracy and efficiency? Baylor's.
Yeah. That's I.
Bellas.
Mhm.
Okay. Mm. So according to Bellas, the neural network potential was more accurate than this reactive force field.
And
More
computation,
accurate.
in terms of computation, and so it is.
And in terms of computation, I don't remember now. Actually, I have to look into it. But I remember that they were more accurate uh, they were calculating some energy parameter and something. So the machine learning potential give you the better result than this reactive force field parameter, because there was some overshooting happening in the reactive force field parameter, as far as I know. I will share one paper with you of Beller. You can go through it.
Okay.
Okay.
And maybe is okay.
Yeah,
Maybe
no.
this reactive force field could give
Mhm.
us the guide to get more efficient neural network. Means maybe one can combine, means in the neural network, if we don't use any guide, means just normal the Weller's
Mhm.
this description of the environment
Mhm.
in general description.
Mhm.
Any means they did not use any pre-knowledge about the system. But
Mhm.
for reactive force field, we need some pre-knowledge. Means for this, is there any pi bond? Is there two pi bonds? So we need to increase
Yeah.
all those parameters beforehand. Okay.
Mhm.
We use this kind of guideline, and on top of that, if we set the neural network parameter, okay,
Mhm.
and
Mhm.
training, then means it will be much more faster, means, and as well as accurate.
Yeah, it will be much faster and accurate. But again, combining this machine learning potential with this reactive force field uh, is another task.
Yeah, I just means this is very, without knowing the topic details, this is just very general comment. Means just
Yeah. Actually, this force field, like, there are so many parameters in this force field. If one could go wrong, then the whole system will blow up.
okay.
Even by 0.5 factor, it will go wrong, then the whole system will blow up.
Mhm.
And then this will be a very big issue. And you'll, like, if you have to see the, like, where you are getting wrong, so that's another level of challenge. So yeah, but we can people are looking for a ways where they can combine this reactive force field with this neural network potential.
Mhm.
Mhm.
Okay. So Subadeep is asking something. Subadeep?
No, just a comment. So the previous self energy term. So I was looking into it. So self energy term is actually the ionization term.
Mm.
Okay.
So it
As
is
far
the
as
contribution from electronegativity and so.
mm.
Okay, there means ionization due to this charge transfer. You are
Yes.
okay.
Mm.
Okay. Yes, that normal. Mhm. Normal force field also take account, but is in another. Okay.
Deepika, just one question. So are there any studies on the spectral calculation using this reactive force field? Still, there are any?
For
Or
VSF.
you are the first one to working on the spectral calculation?
No, it's not like that. If you talk about the interfacial system, so there are studies. Yeah, as far as I remember, for water system, for on graphite water system, I guess there is one paper. So there is one paper, I guess. And apart from that, there are few papers that I can't remember now. But
Means they have done the spectral calculation.
Not the 2D IR part, not the 2D IR part, but apart from that, they have done the VSFG calculation.
Okay.
Yeah. Okay, that's it then. If anybody have any questions, they can ask me directly, or I will share two papers with you in the same group. Hello?
नहीं अच्छा दीपिका तो अच्छा था हेलो
Okay. No, actually, I was quite nervous because this was the first time I was explaining. I hope I explained it like if anybody understood it.
नहीं सही था बाकी जैसा बंसी ने बोला कि स्टार्टिंग पॉइंट के लिए अच्छी शुरुआत है फिर आगे इसको
Okay, I will explain the little components also, but later on, because if I explained it now, it would have gone 3-4 hours.
ठीक है दीपिका मैं फिर लॉग आउट कर रहा हूँ
Okay.